Good afternoon, everyone. So let's start our afternoon session. And I'm glad to introduce the first speaker of afternoon session, Professor Weizhu Bao from National University of Singapore. Will give talk about computational methods for dynamics of nonlinear Schrödinger and Gross-Pitaevskii equations. Thank you very much.
Thank you, the chair. Can you hear me? Thank you. Okay. First, I'd like to thank the organizing committee for the kind invitation. It's really great honor for me here. Come back, this first time to this place, and also this is some kind of a highly affiliated to my Mala University. I graduated from Tsinghua. Okay. So this is joint work with a lot of collaborators here. I don't want to mention all of them. I want to mention the Chunmei Su from Tsinghua, who is also part of this study here. Okay, a brief outline. I'll begin with the Schrödinger nonlinear Schrödinger equation, or in a special case called Gross-Pitaevskii equation. Some dynamical property, including conserved quantity, center of mass, dynamics, and in a special case for nonlinear problem, there's an analytical solution. Then they'll talk about some kind of numerical methods. Classical ones, finite difference time domain method, or FDTD, and also the another one is so-called time split spectral method. One method is have good property like mass conservation, anti-conservation. From mathematical point of view, very nice property, but from computer point of view, very little expensive, and also some other issues. So the another method is time spectral method. There are also different conserve some. Both are so-called structure preserving property. They all, each of them, preserve partial of the conservation laws of the property of the original Schrödinger or nonlinear Schrödinger equation. You will see later. Then we apply the problem, the method to solving a so-called collapse and explosion of Bose-Einstein or BC in short. So my understanding is if you do computer mathematics, you design some good method. You should try at least one example to show, to demonstrate the performance of the method. Then those from applied sciences is convinced they'll use your method. And then also later toward the extension to the Schrödinger equation or nonlinear Schrödinger equation with rotation frame, non-local interaction system, as well as the log nonlinearity, or we call potential or nonlinearity with low regularity. Some conclusion. Okay, here is the Schrödinger equation written here. Okay, so here here psi is called a complex value wave function. I is squared minus 1 comes unit. H bar is Planck constant. M is mass of the particle, and V is the given real potential. So here, of course, if you take H bar equal M equal 1, called atomic scaling, corresponding to in mathematics you do choose a proper spatial temporal length units. And then you end up if you choose the harmonic time harmonic solution, psi equal exponential IET minus IET times U of x separation variable. You plug in, you end up this called time independent Schrödinger equation. So this one, so minus 1/2 Laplace plus V is usually called Schrödinger operator. In mathematics, you remove 1/2 by choose a proper special rescaling. Okay, so this equation was written by Erwin Schrödinger in 1925. Because this work, he was awarded the Nobel Prize in Physics in 1933 together with Paul Dirac. So the equation used to describe the evolution over time of a physical system in which quantum effects, which means the wave-particle duality, are significant in quantum mechanics. So from this equation, it can explain very accurately of the spectrum of the hydrogen atom. So you have the hydrogen atom, there are one nuclei, one electron. So in this equation, you choose dimension x, dimension d equals 3, whole space, and choose v of x, like chosen as 1, maybe minus 1 over with physical quantity, something like minus 1 over epsilon of x, so the Coulomb potential. So basically, you choose this scale. Basically, this from here, and then you choose some physical quantity, and basically this is your potential. So if you solve this one using spherical harmonic, you get all the eigenfunction and also eigenvalue. So and this eigenvalue, you might call eigenvalue. Physics is called spectral or energy level. And this number compared to experiment results of the nuclear hydrogen, they agree very well. Not exact, but very, very accurate. Of course, if you want to do exact match, you must solve Dirac equation with Coulomb potential. So this was this one. So of course, people ask this equation, how can derive this equation? Well, later people use this first formal derivation for use the first quantization of later your second quantization. So you from this the Newton energy momentum law. So we know in classical mechanics, you give a particle move in a potential, like a gradual potential. So E is total energy, P is momentum, P equal mv. Yeah, V is potential energy. So total energy equal potential kinetic energy plus potential energy. This is a scalar. So in this equation, everything is scalar, but formally, physics is the jump. Here you replace E by IH bar dt, and replace P by minus IH bar gradient. You plug in, you end up IH bar dt equal minus H bar square over 2m grade Laplace plus V. Then this operator equation applied to a complex wave function, you end up Schrodinger equation. It's called first quantization. Later, if you replace psi by operator, another, you get second quantization. So this is one way to understand. So that's why you can see so-called in this classical mechanics, E and V, they are scalar, continue continuously. However, in quantum mechanics, in here, like in this Schrodinger operator, right? If V have some property, the eigenvalue E become discrete. So that's called quantized. So that's why so-called discrete eigenvalue, discrete spectral. Okay, anyway. So this shows some formal derivation. And here, if we so since my psi is a wave function, complex, cannot observe in experiment. So physics introduced because physical observable, like a rho equal epsilon psi square, and J is called current. So if psi is of this one, then you define this rho is density, J is current. Then you need to show that rho and J for this continuity equation. In fact, if this equation comes from quantum mechanics, so rho is explained as rho of xt is at time t, position x. To rho is means the at time t at position x, the probability to observe the particle. So normally you have integration of rho equal 1. And of course, I said as I mentioned earlier, if you do time harmonic, time independent problem here for different given V, like a free particle, or step potential V equal 0 here, 1 here, right? Or like a periodic potential block wave, and or like a box potential given a domain omega. Inside is 0, outside is infinite, corresponding to you solve this equation on bounded domain with 0 boundary condition. Or like a harmonic potential. This one is very harmonic oscillator. V of x is taken as x squared over 2. So here shows some kind of so-called, if in one dimension, V of x equal x over 2, you can see psi 0, the density is Gaussian. Then first excited, second one, nth excited, and it's real and imaginary part. Okay, so this Schrodinger equation, the first single particle picture. Later, people by Paul Dirac extend this one to many body, like n-body quantum mechanics. So here, big psi is a 3n plus 1 dimension complex wave function. So here, each xj is the position of the jth particle. Each xj is in R3. So this psi is a high dimension. So this equation is a single particle Hamiltonian interaction of the particle with the nuclei and also interaction between each particle. So this equation becomes called the is very so called many-body problem. It's a key for quantum physics and chemistry, even material science or electron structure, function theory, or even in mathematics. There the study with n go to infinite. What happens? Whether is there a limit, something like that. So this equation is called the Schrödinger equation called non-relativistic quantum mechanics. Later you will see, so from this equation, the wave speed can be unbounded, which is contradict to the Einstein special relativity. There's any particle, the wave speed must be below speed of light. So if in order to do relative quantum mechanics, you go to Klein-Gordon equation, which is for speedless particle, or for if you want to do electron or quark, you must do Dirac equation. So there you will see the wave speed is below speed of light. So in some sense that way. Okay. Okay. So this is the nonlinear Schrödinger equation. So here I write is in the in dimensional form. Of course, when this beta equals 0 and epsilon equals 1 is collapse to plus 1. Okay, this is called dimensionless nonlinear Schrödinger equation or Gross-Pitaevskii equation. So normally, if this is nonlinearity chosen cubic, normally they call also called Gross-Pitaevskii with potential in most cases. If you generate nonlinearity, this is nonlinear Schrödinger equation. So again, here x is my spectral quantity, d could be 3 to 1. If this is the spectral quantity, and the size can be real function, v is real value, and this beta is a given internal constant. If beta equals 0, becomes Schrödinger equation. If beta non-zero is nonlinear Schrödinger equation, and if beta bigger than 0, the induction is repulsive, and the beta less than 0 attractive. So here, what we do is I do two parameters. In fact, these two are not independent. In most physical literature, they always take epsilon equal 1. Beta could be large, could be small. Well, so this epsilon is called scaled Planck constant. So normally there are two cases. One is called atomic scaling. You choose epsilon equal 1. Beta could be large, could be small. Well, if beta large, so this scaling is not used for the interlimit regime. So if beta large, you do a rescaling, that the beta become plus or minus 1. Then you have a small parameter epsilon. With this one, the good thing is the wavelength. And so if beta equal 1 with small epsilon, the wavelength will be in space and time are all at order epsilon. And there pure studies called the WKB ansatz. So this is called semiclassical scaling and semiclassical limit. So if beta equal 1 or minus 1, my first study when epsilon equals 0, how the equation of Schrödinger equation goes to like a Euler equation in some sense. Okay, so this equation comes from Bose condensation of Bose at a very low temperature and produced by Einstein using Bose statistics. And after 17 years, they used the experiment in 1995, and so-called awarded Nobel Prize in 2001 for three physicists. And so for this one, since the n particle identity using so-called Hartree ansatz, the end of this one. So the model derived by so-called mean field theory by Gross-Pitaevskii. So the equation can also use to model so the laser propagation. Even non-Schrödinger come from different applications. One from the quantum physics from n-body problem, mean field reduction. The other from the laser propagation. You can say for my laser propagation, okay, in one direction. So originally it come from nonlinear wave or Maxwell equation. By using time harmonic, you get another Helmholtz equation. Then you in a curved medium. So it seems in one direction, the frequency is very high. The other direction is slow. So by using partial parabolic approximation, you end up nonlinear Schrödinger equation. This is called nonlinear optics. So they are from different community. And in this community, so psi is called order parameter, no longer wave function. Okay, there are other applications like in plasma physics. So it's got the wave interaction between electron and ion. So it's got the like a Zucker system. It's covers between a Schrödinger equation and a wave type equation of quantum chemistry, chemical reaction by based on first principle, for example, Schrödinger-Poisson type equation, and material science or nonlinear or quantum optics in biology, so protein food is studied Davidoff, soliton, or in superfluids. So there, they flow without friction. They also this kind of application. Okay, in order to study this equation numerically or mathematically, normally you do some kind of, it's not numerically, you do after do non-dimensionalization dimension form. So in most mathematical literature, most time either take epsilon 1, beta with a parameter, or you take a beta equal 1 with a small parameter epsilon. Okay, so this equation is dispersive. In something is this equation as a dtu equal lu. The spectrum for L is pure imaginary and time symmetric. So I want to review some problems here so that later there's a different numerical method. Each method will preserve some property structure. Normally, so far there are no numerical method can preserve all of the structure. And time symmetry means you take a t, go to minus t, take a conjugate, the equation doesn't change. And time train invariant, because if you perturb v by real constant alpha, the wave function becomes this one, which implies density doesn't change. And also mass conservation, if in quantum physics, if in nonlinear optics, this quantity is called wave energy, input wave energy. And energy or Hamiltonian is conservation, kinetic, potential, and interaction. And also when v is 0, no potential, there are momentum conservation and also dispersion relation. In fact, for this kind of Schrödinger type dispersion equation, this kind of dispersion relation is very, very important in numerical computation. That means if we plug plane wave xt equal a exponential I k dot x minus omega t, you plug this one into a Schrödinger equation, you end up, so here a is amplitude, k is special wave number, omega frequency. You plug this guy into a Schrödinger equation, this one here, you end up omega of k equals this one. It's called dispersion relation. Then you can see from this one you take a c of k called group velocity. C of k equal gradient of omega of k, which equal epsilon times k. For any fixed epsilon, k is special wave number. K can go to infinite. So you can say when k go to infinite, c, the wave speed, is unbounded, which implies the Schrödinger type equation is non-relativistic. Because if it is relativistic, then the wave speed is always bounded by speed of light. Okay, if in one dimension, when beta less than 0, they are so-called bright soliton. So like this one, so it's like a tangent function. So this function, you can see at the far field, the solution decay to 0 exponential fast. So this kind of solution is like a two bright soliton interaction. It's very easy to solve numerically. Since it's a decay to 0 exponential fast, you truncate the bounded domain with some boundary condition. You can job is done. And the other case is beta bigger than 0. Interaction is attractive. Oh, sorry, repulsive. This is attractive. Then you can see there are so-called dark or gray soliton. So when psi of t equals some kind of a is a bigger tangent function plus something. So this kind of function you can see when at the far field, the solution is non-zero. Since tangent, right? One side is 1 minus 1. And so due to this I kx, when x go to far field, kx becomes very large. So the solution at the far field is non-zero and highly oscillatory. So this kind of problem, if you solve numerically, when you truncate the bounded domain, you must choose the proper boundary condition. Luckily, this equation, right, itself highly oscillatory. But if you compute the partial x psi, which tangent becomes a derivative of a synchrony function. So the dx psi goes to 0 exponentially fast. If you solve this kind of problem, in whole space, right? If you try to bounded domain, you use kind of the Neumann type boundary condition, not delicately. Then you can solve very properly. Of course, recently, so PD people also study, or mathematical study, so the rocket wave. That kind of solution at the far field, decay quadratically at far field. Okay, this kind of solution. I show one example. You can show this is kind of this one dimension. The Schroedinger equation is kind of integral system. You can see here what I plot here is this is my x. This is my rho of xt. At the t equals 0, I have one soliton, bright soliton, another bright soliton, and my beta equal 1. You can see when time evolve. So before the two solitons meet each other, they move towards each other. Their profile doesn't change. The soliton, because when they meet each other, they interact and generate some sound wave. And interestingly, when they after interaction, they separate completely. This is one of the phenomena of the integral system in one dimension. Okay, another example is one interaction of two dark solitons. You can see here is my, again, x. This is my rho of x density. Again, you can see at the far field, the density is non-zero. So this is one, another one. This thing like they have a non-zero background of the system. You can see initially I have two dark solitons with the same height here. Of course, you can see when they initially one doesn't move, one will move towards right. You can see when they meet, they interact. Then, if you do carefully study the phase, the initially at the left one, they meet, they penetrate. So this is kind of interaction is completely different with the classical mechanics. See, classically, if you have two classical particles, so one stay here, the other same mass, they will fix speed, right? When they put kid here, this one will go, this one stay here. But this this kind of quantum system here, you have two waves. This one go, then penetrate. This one stay here. Okay. So this is one dimension, very simple spectral inertial data. So this very nice interesting. Yes. Well, you can use the phase to check. You can compute the current and the velocity. Let's say similar phenomenon for this dark one. Yes. Yeah. This is they check very carefully numerically. Okay. Of course, you can see for this one dimension, no potential, spectral in the data, there are some very nice phenomena. Of course, in many applications, V could be very special. And normally, like a Gaussian different initial data. So one people study how to design some efficient and accurate numerical method to solve this problem. So of course, to solve this one, there's some, so you know, the problem is dispersive and nonlinear. You know, to solve a dissipative system, numerically can always add more dissipation. So it's stable and accurate. But for dispersive, if you add some dissipative term inside, you lose mass conservation or anything. And also the solution could be, so the solution and also the potential V, they could be smooth, but also can be singular. And also they will be highly oscillating. This will show here is one, this is my X, my density. You can see the solution is, if you zoom in, it's smooth, but the wavelength becomes smaller and smaller when epsilon becomes small. So the aim of design numerical method is to keep the property of the original problem at this level as much as possible. Like a time reversible, we find this time reversible, time invariant, and also deregulation. For this kind of, especially when the frequency wavelengths become smaller, they are most important. Of course, mass conservation and conservation. Of course, in high dimension, also challenging too. And the aims to design efficient actual numerical method of this method could be explicit or implicit, which depends on computer cost. And also like spectral temperature resolution, accuracy and stability. Also, in our study, we are also particular attention on how the resolution of the neural method when at the strong internal regime. So either when my epsilon equal 1, my beta much large, like beta equal 1,000 or even larger. You imagine like cold atoms with million atoms there. Or when beta equal plus or minus 1, but my epsilon small. Question is how each method, their performance, when epsilon goes smaller, for this method, for the given method, how your mesh size time step depends on epsilon. Okay, of course, in the literature, there one is called chronicity difference method, very popular. Basically, just for simplicity, I use one dimension as an example, consider bounded domain with zero boundary condition. So the method can be traced back to 1986 or something by this Tony Chang and Long Junshen and a lot of like Bob Galassi. He's the first person to show this method is first order convergence in time, convergence in space time. And later, like I think it's Chen Sun Chang and Bo Ling Guo and Hong Jiang, they show second order convergence. So the method is very simple. I don't want to. So basically, in space, in time, you do second order like a trapezoidal rule. In space, central second order central difference. Only difference is for this nonlinear term, you do a special average so that this scheme can have properties mass conservation, energy conservation. So the scheme, of course, it is implicit. From Tn to Tn plus 1, we need to solve a fully coupled nonlinear system. Obviously, one dimension is simple, but high dimension you need a lot of work. And the scheme is time reversible. Time reverse is not. Mass conservation is yes. And this is maybe the only scheme which can mass conservation, energy conservation. And dispersion relation is not preserved. Accuracy formulae in space is second order, in time second order. So I think at the beginning of this century, people study and try to understand for this scheme, when epsilon small, what's the resolution? When epsilon small, with epsilon smaller, your mass size h and the time step tau at which ratio of epsilon? Understand the resolution, so that your numerical method is accurate. So they found by Markovich, Paula, and Mauser, they show that for this different scheme, your h must choose as little o epsilon, and the tau times tau also little o epsilon. In computation, you need to choose h equal epsilon square, tau equal epsilon square, so that your result is trustable. But this is way below, because under resolution scheme, we know a scheme, right, have optimal of resolution, means your wavelength, your mesh size, or time step is at the same order of the wavelength. It's by Shannon's sample theorem. You want to capture a wave, you need 35 points per wavelength. Okay, of course, error estimate. So for this one, in one dimension epsilon equal 1, there are this Bob Galassi and they have studied. Basically, they show that the scheme by L2 norm and H1 semi-norm is both second order in space and time, but fixed epsilon. What is the key point proven here is, so we'll prove numerical scheme, right? Well, the key is to show that the psi Jn, the numerical solution, is bounded. So for in one dimension, for this one, they use one key included is like for any function in H01 omega in one dimension. So f, the L infinite norm, is bounded by L2 norm and H1 semi-norm. Since mass conservation, energy conservation. So the numerical solution psi Jn both are bounded. So psi n, Jn is bounded. So use this one. However, this technique cannot be extended to high dimensions. This is not valid in 2 or 3 dimensions. And also for non-energy conservation scheme. So by using so-called some kind of energy method, and also so in 2 dimensions, what we joined with Yong Cai, we prove some kind of error. The key is how to prove our numerical solution psi n is L infinite norm. It's bounded. So what we do is using this analytic solution. This one is always assumed bounded, and then using the arrow. Since you can see we have a numerical method. If that solution is bounded, if your solution is the method is converged, the numerical solution must be in a pipeline close to the analytic solution. So this is arrow. So then you can use this because for the chronicity type scheme, we use a kind of cutoff function technique. And for like a semi-implicit scheme, use this mathematical induction to prove. So since you can see this is bounded. If the solution is like you have some arrow for this step. You after one step, this one is bounded, then this one by some mathematical induction can show it's bounded in some sense. Okay, so this method has very good property, but unfortunately scheme when absolutely small, the performance is not good. So then at that time, at like maybe 20 years ago, 50 years ago, people want to study, find a good method which can have much better so the resolution, absolutely small, or have better performance in a semi-classical regime. So at that time we also try to another method called time split method, which say from time t into t plus 1, what to do is you first do a splitting. So what you do is you first describe so-called free Schrodinger equation. For this one, good thing is you can see this is a constant coefficient PDE. If you have a proper boundary condition, you can find the Laplace operator with the given function, the eigenfunctions. Then you can do use the spectral method. You can in phase space. This the corresponding ODE become decoupled and linear with the constant coefficient. Then you can integrate in phase space analytically. Then for the second step, you can see this, you solve this one. So this one somehow you can easy to show that at this step, at a pointwise for each fixed x, the dt absolute set square is equal to 0. Since this guy is pointwise, the density is conserved. So you plug this property back into this one, this non-regularization to the property. So this becomes a linear OD pointwise. So you can integrate analytically, you can solve this one. And this method was given, so when epsilon equal 1, it's very early. But we find this scheme have very good resolution in so-called in the semiclassical regime. The scheme has good property. Computational is very efficient to the Fourier transform, and time reversible, temperature invert, yes. Mass conservation, yes. So L2 stability, no issue, and also different relation. As long as your number of points is bigger than the given, so wave number key, and basically for plane wave, you can achieve a next solution. And energy conservation, of course, not conserved mathematically, but if your time step not too big, you observe very accurate. So most cases is this relation is preserved. Okay, and of course, fixed epsilon. The scheme is spectral accuracy in space and second order in time. We can do higher order too. And we find that the scheme for physical observer, in order to compute the density rho or J accurate. Interestingly, for linear case, for beta equals 0, you need to request H. The measure size H equals bigger or epsilon. The times tau can be chosen independent of epsilon. This is surprising. You think the solution in time is highly oscillatory. If you only choose density, your times tau can be chosen independent of epsilon. Somehow for linear case, this method, if you only interested in the density, there's so-called super resolution property. And of course, for weakly, similarly, for strongly, if beta equal order 1, then your H and tau equal epsilon. So that means, so this scheme, if for so-called when a semiclassical regime, even for strongly, for the entire case, they have so-called optimal resolution in terms of the observable, observable. And for linear problem, if you only choose observable, they have some kind of super resolution in time. And this at that time as a surprise a lot of some kind of to a lot of people in some sense. Okay, of course, error estimate. Again, we'll talk about for epsilon equal 1. And of course, a lot of study from from Bose, from Chris Lupich, many others. And again, for linear case, for beta equals 0, one can prove the En is the error function. One can prove that the L2 norm for this method less equal C of t, h to the power m plus tau square. Well, m depends on the rate of solution. Interesting here is this C of t grows linearly with t. Remember, C of t equal somehow C1 plus C2t. Then, in fact, this one can understand here is due to this split method, which is a unitary flow in L2 norm for this Schrodinger type equation. So this is very interesting. So you can say for this linear problem, right? The error in L2 norm is less equal C of t times this one. So here we give it the error depends on the mesh size times tau and the length of time interval t, and this C of t grows linearly with t. In some sense, if you for this problem, if I do long-term computation, you can see if I refine my mesh size or time step by half, I can compute so 4 times longer here tau square with the same given tolerance since here C of t. Because for nonlinear problem or for many other problems, if you want to use the ground inequality, this C of t normally grows exponential with t, then cannot do long time. Okay, so this also numerical computation also confirms that this kind of three methods, they are good for long-time computation. This shows why, because this constant C grows at the most linearly in this. Of course, you assume the end solution is somehow bounded globally, in some sense. Of course, for nonlinear problem, we can only prove this C of t can only grow exponentially. Of course, here, if even for linear problem, if you use H1 norm, sorry, C of t also grow exponentially. You cannot, with this you cannot prove. Okay, of course, how to prove this method? The error bound depends on h, tau, and the small epsilon. It's still very challenging because you need a lot of, especially you try to prove some sharp error bound which conform numerical observation, but still challenges in there. Okay, I can skip this one. There are many other methods I do not show. So you have this method. So at that time, we try to apply the method. So from here, you can see that among many other different numerical methods for the non-Schroedinger equation, the times method seems to perform very well. Number one, from accuracy, it's very efficient. Accuracy also good, and also have something that can preserve the mass conservation, time symmetric, also dispersion relation, and a good resolution with absolute small. So at that time we try to solve a problem at that time, so-called a three-dimensional collapse and explosion of the Bose-Einstein BEC. So there the problem is the following. So at that time, we know for this nonlinear Schroedinger equation, if you ignore last term, if the beta less than 0, if in 3 dimensions, mathematics can prove that this problem, if the initial energy is less than 0, the function blow up. So for this problem, if you 2 or 3 dimensions, beta less than 0, called interaction, attractive. So phase one try to observe this blow up. Is mathematics prove their blow up. They want to observe this blow up in experiment. So what they do is the following. They at t equals 0, they collect some kind of rubidium atom, like 16,000, with repulsive interaction. So basically here, my beta equal 4 pi n as over xs. xs is a special dimension unit. As called astronomical length. So they use to take a rubidium 87, as natural is bigger than 0. So at t equals 0, they collect 16,000, cooling down, get a ground state. They fix the V, fix the beta, positive. You have a ground state as initial data. Then at t equals 0, like here, this is my as, this is my time t, and this is my as. Yes, and initially as equals a initial, positive. And then at t equals 0, they suddenly change as from initial positive to a collapse negative. Then it goes down. So they observe that here dot from experiments. You can see the system, the number of particles they conserve for t collapse time. Then the system decreasing. So this shows that this nonlinear Schrodinger equation, if beta small, beta less than 0, if you want to use one to model some system from quantum physics, of course this one is only valid for short before blow up. Because if after near blow up, this system, this model is no longer valid. The reason is the following: because physics show that the experiment show that the mass not conserved. Physics explain the following: you can see the origin have 16 16,000 atoms. You have 3 times 16,000 dimension system, linear Schrodinger, mass conservation, energy conservation. For high dimension Schrodinger equation, of course, no blow up, linear problem. But that's too high. You do mean field, you do Hartree approximation. So the assumption is you assume that the density not too high, and also the distance between two atoms not too small. However, since beta small, less than 0, it's an attractive interaction. So the particle go to the center. The density at the center become larger and larger. And then the distance between two particles is smaller and smaller. So then those some interaction, like in elastic interaction, is important when the center becomes too high, but it's still when the system ignored. So physicists propose, oh, okay, you add a quantic damping term. Because here beta is beta same. The delta 0 is a universal constant. This is a model proposed by phenomenology model. So we use, so this is kind of a snapshot to show the density. So this last term model is called the 3-body recombination loss. So we use at that time we use the same physical experimental data, 3 dimension, the same quantity, and then we solve it using this splitting method, using somehow 2048 cube grid points at that time, but some kind of 1 month simulation. Okay, so this is somehow experimental result, some snapshot for numericals. Because if you come to this one, if you rotate the parallel 2, quite similar to the other side, and you can see the central density. This what I show here. You can see this is t equal, this is time. This is the total number of particle system. The constant, the decreasing, the one jump decreasing, the almost constant, another decreasing continue. And you can see that this is the plot here is the psi of 0,0,0t square. You can see initially it's very small, go big, go down. So basically from simulations they show a sequence of collapse. Okay, this is the AS. And here is what the plot is. This one is when A collapse, taken as minus 30 A0. A0 is some fixed quantity. So the star is experiment. And the dash is from star, they do physics, they do interpolation formula. And the solid line from the simulation. And this circle is when A collapse equal minus 6.7 A0. And the circle from experiment. And also the dash line is from the circle line to interpolation, solid line from simulation. And this is when A collapse equal minus 250 A0. And since the canonical two experiment, they use this dash line extrapolate dash line here. And the solid line is our simulation. And in other simulation, the delta 0, this one is universal. Using one simulation, fix this data, choose delta 0. The delta 0 is used for all other cases. Okay, so here a movie show how the simulation. You can see what I plot here is so-called the density absolute value of psi x y equals 0, z and t. T equals 0. You can say blue is 0, the red is so-called large value. So basically at the initial t equals 0. So the beta is bigger than 0. So the contour plot is some kind of ellipsoid, something like this one. You can see when at t equals 0. So since my interaction since my interaction is attractive, you can say particle go to the center. So go to center, so due to attractive interaction, particle go to center, the density will explosion. Then when the density too high, the damping term, which is psi to the power 4 times psi, the damping term takes over, they collapse. So it's a sequence of explosion, collapse, explosion, collapse. So at that time we have this result, which agree with the experiment very well. Even the one of Nobel Prize, I think the Edward Cornell, they ask our simulation result to verify with simulation with experiments. Okay, due to time on the so with this kind of application to the experiments, always go advanced. We need to produce a new set up a new problem. So next problem is the Gross-Pitaevskii equation or natural equation with the angular rotation. So the model is like you have one more term minus omega LZ. So we know P equal minus I gradient is the momentum. L is x cross P in 3 dimensions. 2 dimensions, just take if 2 dimensions, just take the 2 term setup. Okay, so this LZ is called z component of this L, which is if the constant coordinate is basically minus I x dy minus y dx, or if in 2 dimensions you use the polar coordinate is minus I d theta. RC is polar coordinate. Okay, for this one, of course, you can say precisely this term consequence is very simple. The other term is is algebra function. But with this one, since it's x dy y dx, it's tough to challenge it. So what we find, what we do is we use a rotating logarithmic coordinate. The idea is very simple. You can see a system, right? The system is very challenging. You find the system setup is you have a condensate inside. There are 3 lasers, they rotate. So what do we find? If you introduce a rotating coordinate, this is my xy coordinate. I introduce this x theta equal a of t inverse x, where a of t is rotating matrices. The angle is omega t. So it's something here. Because in 2 different, this is my xy, this is my x theta, y theta, and the angle is omega t. Then straighten similarly. Then I do it. The phi is this one. Then you do this variable back to our system. Then you can say this equation will be reformed to the following I dt phi equals this one times this one. This bad term disappears. In return, we have this v is time dependent. So you can say for this one, if we solve it by this simple method, you can say first step is first same. Second step solve this same since v is real. This one can also solve analytically. So in something here is okay for same problem. You can see this one and this one mathematically they're equivalent. However, if you want to design a neural scheme, if you based on this one, this term causes a lot of trouble. But if you based on this one, all the gone. You are much easier. So basically, if you want, so for same problem, there are different mathematical formulation. If you choose a proper formulation to design your neural scheme, you will do. If you choose a good formulation, you will do a much better job. Okay, I just show for this one. I just show one similar result. Is this show some kind of what is lattice? We have this one with so each blue is 0, each blue dot is a quantized vertex center. We have many vertices with a potential given potential. They have with this method that works very well. High order scheme. Okay. Also recently there's with so-called non-local interaction, or they call dipolar quantum gas. The model becomes one more term lambda u dipole conserved square. Well, u dipole is somehow equal, okay, if it's 3 dimensions. Here n is a unit vector in R3, like a 0, 0, 1. And the u dipole of x equal constant 1 minus 3 n dot x over x squared over x cubed. So some subsequently have a lot of molecule by applying external electromagnetic potential. So 2 atoms, 2 molecule form to a dipole, like a polymer. Polymer means they have direction. So all these polymer, they are aligned same direction. Then cooling them down, they have this called dipolar quantum gas. But the dipole, the interaction is sort of non-local and also anisotropic. You can see this kernel, again, is highly singular. Because as x go to -0, this is like a big O, 1 over epsilon x cubed. We know Coulomb is 1 over epsilon x. This at the origin is highly singular, even singular. But interesting here, 1 minus 3. This is very important. So this shows that so this kernel, along any sphere surface, the integration is 0. Okay, so for this one, again, we find a nice formula. If you let the R epsilon value, dn equal n dot gradient, n is unit vector. This kind of directional derivative. And then u type can be decomposed a local one and this one. So then this interaction can be u type convolution become this one. So this phi is convolution. So phi is a Poisson equation. So you can reform this one to a Gross-Pitaevskii, a Poisson type equation. Because all the rest are same except here 3 lambda dnn phi. Well, this little phi is minus lambda phi square equals psi square. It's Poisson equation in 3 dimensions. Interesting here, if this v is anisotropic, then if strongly confined in z direction, this one can be 2 dimension. The 2 dimension, this one is the same, but this one will be replaced to a square root Poisson type equation, like a fractional type. So this one corresponds to 1 over epsilon x in 2 dimensions. It's fundamental, something like that. Okay, so this one with this kind of PDE formulation, you can design all kinds of different methods. With this convolution, normally people use the Fourier transform, which causes numerically there's the numerical locking phenomena. But with this again, with this new formulation, so-called we have designed a lot of very good efficient methods. Okay, so this I can skip. Well, recently, a few minutes, 5 minutes, just we do something like the log Schrodinger equation. So the problem like the IDG psi minus Laplace psi plus lambda psi log psi square. Okay, here of course there's a log nonlinearity f rho equals log rho. So this one, of course, when rho go to 0, log rho go to minus infinite, which is unbounded singularity. Of course, from this f rho, we can define the capital F rho, which is the integration of this one. This one will appear in the energy functional. Then to this, so let's solve this one due to this singularity of this f rho. The numerically, if I want the numerical scheme, of course, there are a lot of PD study for this one, like a scattering. So a lot of some like a Gaussian solution of this one. We are aiming to solve this numerically by different numerical methods, and also what's the error bounds. So what we do is one is to recognize f rho directly. So like replace f rho of log rho to f tilde epsilon rho equal log epsilon square plus rho. One way to do it. The other way is using f hat epsilon of rho equal log epsilon plus square root of rho square. There are 2 different ways to do it. But then of course you have then you replace f this term by this one or this one. Then the question is, for the regular equation, how the arrow between solution of this the regular equation and the original equation depends on epsilon. Then you solve the regular equation. Your error bounds may depend on mesh set, time step, and also epsilon. How the error bound depends on this small epsilon explicitly. Well, later we find that instead of recognize this nonlinear f directly by this one, a better way is to recognize the energy function capital F rho, which is given here. You can say this one, when rho goes to 0, minus infinite, not good. But this capital F rho, when rho goes to 0, becomes 0. Then the capital of rho, they continues to up to rho equals 0. So what we do is, say for capital F rho, what we do is from the interval, like say when rho greater equal epsilon square, epsilon is a regularization parameter. So when rho greater equal epsilon square, we just take f rho itself. Then when rho between 0 and epsilon square, we replace this function by a polynomial. So we request this function fn of epsilon rho, which is Cn, basically at the rho epsilon square. Because the epsilon here is somehow the amplitude of the wave function at the something like that. So we request this one as a Cn of n equal 2. So we find out this one. The arrow of this scheme for the wave function is similar, but for the energy approximation, this one is much better than this one. So in some sense, if you're interested, you can refer to some paper here. And also we can talk about the long-term dynamics. So we consider the Schrodinger equation with so-called the weak nonlinearity. So we have small pair epsilon. Epsilon could be 0, 1. It can be small. But we consider this dynamics up to t sub epsilon, which is t0 fixed over epsilon square. So this epsilon somehow you can think is so-called okay, if you do a rescaling, like phi equal epsilon psi. So then you can see you get the classical Schrodinger equation. That Schrodinger equation with inner data, which, well, the density of the inner data is order epsilon. Well, the amplitude of phase 0 is order epsilon. So in some sense, the Schroedinger equation with the weak nonlinearity and order 1 inner data is equivalent to you have a class order 1 nonlinearity, but a small inner data. So this epsilon means the amplitude of the wave function at inner data. So of course, for this kind of problem, you need to consider long-term dynamics. Consider the order up to order 1 is trivial, but up to long time, so that the interaction comes. Of course, if we do a change another rescale that s equal epsilon over t, this problem become a highly oscillatory PDE. Of course, this one is different with the semiclassical. So this way you can see the wave in space is order 1 wavelength. In time epsilon square, and the wave speed is 1 over epsilon square. That means if you do whole space problem, if you do come to a long time, you come to domain, the length must be 1 over epsilon square. Okay, for this one again, we can first for this long time dynamics, for this different method, we want to do some error estimate. We find up to long time the error bound less equal C0, which is constant interval of h, tau, and epsilon. But like h square over epsilon square, tau square over epsilon square. So even for this one, we know wavelength is in space time is order epsilon, order 1. But in order to do long time, your h mesh size and times of tau must be order epsilon, which is under resolution. This is interesting. So each step is the same, but you do many times. Since you can say here my n times tau, which is not classical, is bounded. But here is n times tau equal big O epsilon minus 2. Then we find for this, if you do use the splitting method, the error bound is like C0 times HM0, regularity of different solution, plus tau square, which is uniform up to long time. And but this is our first proof at bounds. When we do simulation, we find the results is better than this one. By careful study, especially we use called regularity compensation oscillation. Basically, for high frequency, we use regularity to estimate. For low regularity, for low frequency, we use some kind of physical translation using the splitting method have some property. We can prove that the error bound that's equal C0 HM0 plus epsilon square tau square for this n of a long time. We show that somehow you can see epsilon smaller, you do longer computation, long interval computation, but the error depends on tau uniform. But when epsilon smaller, the error becomes even smaller, and the numerical confirm this one. And of course, so this one. And very recently, we also considered the Schroedinger equation with the low potential nonlinearity. So my potential V. Okay, classically, so my potential, for example, my V become well potential, like 1, 1, 0. So V is on the L infinity. Or if V take a Coulomb, 1 over epsilon of x. So V is on the L1. In this case, my solution psi is on H2. So like a well potential or step potential or Coulomb potential. Or my F rho, take it as F rho equal beta times root of power sigma. Sigma between 0 and 2 not equal 1, like a Li Huang-Yang correction, something like that. So in this case, my solution psi is on H2. In this case, many numerical methods like a finite difference, they may converge, but no converge rate. Then we find this in this case, this splitting method with some proper modification, they can achieve the optimal convergence in response to the regularity of the solution. Like for example, if psi in H2, we can prove the error in L2 norm is second order in time. If you're interested, you can find some results here. And so some take-home message is for this kind of dispersion PDE, especially is highly oscillator or some kind of problem. The stability is one issue, but the most challenging is resolution. And whether your method have some kind of either resolution or either long-term behavior, so that if whether your method can preserve this kind of dispersion relation and time symmetry is very important for your performance. So I have some conclusion here. So I just brief this equation and some property. So basically, if you know more of the property of the problem, and embed this property into the design of your scheme, you can do better. And there are some challenging, like some couple equation, like a couple of the Schrodinger equation with the Boltzmann equation, or some other dispersion PD, like the Dirac equation, and also, for example, with the random potential or high dimension through this kind of like a machine learning or deep learning methods, or through the using so that you have this like a quantum problem. It's a natural problem by using quantum computation algorithms. Hopefully, if a quantum computer arrives sooner, there are a lot of interesting work there can be done. Thank you.
Thank you very much. Any questions to the speaker? Okay. Yeah.
Oh.
If I understood correctly, the only 3D result you presented was the one that took a month to compute. Is that right?
So, sorry, say again.
You mentioned a 3D computation that took a month to compute.
Yes, 15 years ago.
Yeah.
Now maybe just 1 day or 2 days.
I see.
Yeah, that time, yes. But now we don't do parallel. It's like a 2048 cubic points. But we need to solve up to t equal like 50, something like that. Yeah. Yes.
And so most of the other applications you presented were in 2D?
Yeah, there are a lot of other applications. For example, what is dynamics?
Yeah.
And also a lot of people do this kind of like code items for control system. Also, people saw random. There are a lot of applications there. Yes.
Okay, thank you.
Yeah, thank you.
Any other questions?